Tēnā koutou katoa. It's going to be a little bit change of subject. So my research is in high energy neutrino astrophysics. So when you think about astrophysics or astronomy, you probably usually think about optical telescopes and detecting optical light to view our universe. But there are other particles, I call them messengers often, that can give us complementary and sometimes unique views of the universe. And the particle that I like to detect is the neutrino. So before I talk specifically about neutrinos, I want to talk a little bit about the area that my research falls broadly in, which we call astroparticle physics. So it's a fancy name to make us sound clever, I guess. It is the synergy or the interface between both particle physics and astrophysics. So in the particle physics domain, we're trying to answer some of the questions that are also approached by facilities like the Large Hadron Collider at CERN in Geneva that you might have heard about or at least seen some images of. So there they accelerate particles to high energies, crash them to see if they can approach the physics that governs those highest energies and whether the theories that we have currently are the appropriate ones at those really high energies. So my research, we want to do similar things, but we want to go to higher energies, so we don't use accelerators on Earth, we use the universe's accelerators. So out there in the universe, there are accelerators to much higher energies. And we want to understand those environments, those really high energy places out in the universe, and so we have to detect particles that are coming to us from them. So that's the broader context of our area. To do this kind of research requires really large detectors, telescopes, observatories, and equally large or large numbers of people to design, run with those detectors. So the collaboration I work with is called the IceCube collaboration. It's around 300 scientists over 50 different institutions around the world. And I say that I really enjoy working in a team. I really like, I'm a team player, I've played lots of team sports, and I really like working together with other people and that way that we can achieve things that any one person could certainly not do on their own. So we can really get to those big questions by working together. And so one of the questions that we are trying to approach is to improve our understanding of cosmic rays. So where they are coming from and what accelerates cosmic rays, or what gives cosmic rays their energy. So firstly, what are cosmic rays? So they are high energy particles that permeate our universe. They come in a wide range of energies, and so at the lowest energies, cosmic rays are coming from our sun, and they are what creates the phenomena of the aurora that you might have seen recently. So those are also cosmic rays, but just accelerated within our sun. There are much higher energy cosmic rays, 1 million times more energetic than we have managed to, humankind has accelerated at that Large Hadron Collider in CERN. So the universe is capable of accelerating particles to much higher energies. But at the moment, we don't actually know where those particles are being accelerated, although our research has actually now just recently started to answer those questions. Where do I point? So the reason it's hard to know where cosmic rays come from is because they're electrically charged, and charged particles are bent by magnetic fields. Their path is distorted and twisted by magnetic fields. And there are magnetic fields in our galaxy and throughout the universe. So the cosmic rays that are accelerated somewhere, we can detect them on Earth, but even though we can get the direction that they come into Earth, but that doesn't tell us where they've come from. Over here. But cosmic rays, we know that some of them, not all of them because we detect them, but some of them will interact at their source. And inevitably when cosmic rays interact, they produce these particles called neutrinos. Neutrinos are neutral and they travel on straight lines. So if we can detect those neutrinos associated with where the cosmic rays were produced, then that will be able to tell us about those sources, identify those sources, and study those neutrinos to tell us about those sources. So that is the reason. So just before I go on and tell you a little bit about detecting them and what we've learned, I'll talk a little bit more about neutrinos. I was interviewed on the radio a couple of years ago, and I said, do you know what neutrinos are? Thinking, no. So I tell you a little bit about neutrinos. They are elementary particles, which means they can't be broken down into anything smaller, very much like the electron. So if you've heard of the electron, just think of a neutrino like the electron, but they have a very crucial difference, is that the neutrinos are neutral. So the electron has an electric charge, but neutrinos are neutral. And that difference means that they hardly interact at all, very, very weakly interacting. So they're sometimes called ghost particles because neutrinos can just pass through solid objects, in fact, right through the Earth. So the sun gives out neutrinos, you actually give out neutrinos, and you won't know that the person next to you is producing 340 million neutrinos a day because they're just passing through your body. So neutrinos are these ghost particles that can just pass through solid objects. So that makes them very unique messengers because we can see into objects in the universe that nothing else can escape from. But the fact that they hardly interact at all means that you need to have a very large detector to capture them, because if they don't interact, you learn nothing about them. They need to interact so that you can detect them, and then you want to get their energy and the direction that they've come from. But to do that, they need to interact. So because they interact so rarely, we need a very huge target of material that we will hope that our neutrinos might interact in. When neutrinos interact, they produce other particles, and those particles produce light. So what the IceCube collaboration has done is we have instrumented a cubic kilometre of ice below the South Pole. So because if we want to detect light, it needs to be transparent, our target material, and the neutrinos will interact, produce these charged particles that produce light, and so we have a cubic kilometre of light sensors ready to capture that light. So they are below the ice at the South Pole, just at the South Pole because that's some ice. It could actually be in the ocean, and there are other neutrino detectors in the ocean, but it's helpful to have them in the ice because they stay in one place compared to being in water, and so we've been the most successful neutrino detector. So once we had completed building the detector, which took 5 summers, we wanted to detect these astrophysical neutrinos that I mentioned. I'll just show you an image of, if you could go down into the ice, something like what you would see, our array of sensors waiting for neutrinos to interact, produce particles and detect light, that we will then, from the pattern of the light and the amount of light, be able to deduce the direction and energy of the neutrinos. So our first target that we wanted to detect was these astrophysical neutrinos. Those are the neutrinos produced where cosmic rays are accelerated. And these have been postulated because cosmic rays should interact near their source, but no one had detected astrophysical neutrinos before. And soon after we had completed the detector, we were able to detect these neutrinos, which was recognised as a breakthrough in our field. So we had detected neutrinos, so what did we learn? We learned something about because of the energy spectrum, but we detected that they spread across the sky. So that told us for a start that they weren't coming from our galaxy because they weren't correlated with our galactic plane, with the Milky Way in the sky. They were spread all across. So they were coming outside of our galaxy, but there were many of them. So there wasn't single isolated sources. There were very many sources. But we tried to correlate them with known objects, known astrophysical objects that have been detected with optical light or gamma rays, high energy photons, but they didn't seem to correlate. So there were many